Good morning, everyone, and welcome to the first technical session. My name is Susan Dumais. I'm a technical fellow at Microsoft and the director of the research labs in New England, New York, and Montreal. In this session on machine learning conversations, I'll be joined by 4 researchers from Microsoft who are really pushing interesting new frontiers in reinforcement learning and natural language generation. My colleagues will be Katja Hofmann from the MSR Cambridge lab in the UK, Akshay Krishnamurthy from the New York City lab, Asli Celikyilmaz from MSR AI in Redmond, and Dan Klein from Microsoft's Semantic Machine Research Group in Berkeley. Katja and Akshay will lead us off by talking about some recent theoretical advances in reinforcement learning that enable both more efficient and adaptive systems to be generated. And Asli and Dan will talk about new results in language generation for both creating coherent long-form stories and for composing sequences of actions in the context of conversational AI systems. Each speaker is going to give a short talk, followed by questions from me and you, the audience. The audience can use Hub to ask questions. We'll be monitoring that throughout. And without further ado, let's take it away with the first talk by Katja.
Welcome to my talk on one of the most exciting frontiers in machine learning, learning to adapt advances in deep meta-reinforcement learning. To motivate the problem of learning to rapidly adapt, I want to give you a little bit of context on what my team and I are currently working on within the Game Intelligence Group at Microsoft Research in Cambridge. Our mission is to advance the state of the art in machine learning in order to enable new applications in the gaming space. In particular, that means that we envision new game experiences for players, and for developers, we create new tools and capabilities so that they eventually will be able to use machine learning to shape those new and engaging experiences. Within this space, we see one frontier that is particularly exciting and that, if solved, will have a lot of applications both in gaming and beyond. And that is the frontier of developing machine learning approaches that can rapidly adapt to new scenarios, or in our case, to new players. Just to give you 2 examples, if we think of a game like Minecraft, there's an enormous amount of diversity. And so if we wanted to use, for example, machine learning-based agents in order to solve some tasks or collaborate with players within Minecraft worlds, they would have to be able to very quickly adapt to new situations that they might not have encountered before. Just to give you an example here, there is one way in which people play Minecraft, which is called a parkour. So it's essentially a speed run where the agent has to very, very quickly run through a parkour that in many cases human players have created for their friends or possibly for agents. Now, just looking at these few examples that I'm showing you here on the slide, you can see the enormous diversity of those kinds of tasks. And if you wanted to imagine an agent that is able to solve all kinds of parkour challenges, it might have to deal with situations that it has never seen before, just based on the creativity of the people who create those kinds of parkour challenges. Very similarly, in a game setting, we may want to have agents that can very quickly adapt to the enormously varied play style of the diverse player population that play Xbox games every single day. And so a key challenge that we're looking to address in our current research is to understand how machine learning-based agents or models could very rapidly adapt to, for example, new game scenarios and players, in particular in settings where we have limited data available for each individual player or for each individual game setting. Now, to put this in context, at the moment, we have seen a lot of rapid progress in reinforcement learning and imitation learning. So we are now able to train machine learning-based models that can very effectively solve a given task. Just to give you one such success story, here is a task that we posed to the research community last year at the NeurIPS conference, and which will be repeated this year at NeurIPS 2020, which is the mineral competition, where we collaborated with partners at universities, for example, Carnegie Mellon University, and other partners in order to create a challenge that would really test the ability of current reinforcement learning and imitation learning approaches to create agents that can show complex behaviors. And in this case, the challenging task that we picked was to obtain in Minecraft a diamond. And so, in case you're not familiar with the game Minecraft, in order to obtain a diamond, a player or an agent would have to go through a quite complex sequence of steps. For example, gathering wood and other raw materials, create tools, and eventually it needs to start digging, find a cave, and find a diamond ore in order to actually mine a diamond. And when we set out to kind of pose this challenge, we were concerned that this task was too hard and that it would take a very long time for people to actually solve this. And we were very positively surprised to see that within the first iteration, the competitors really rose to the challenge, and they were able to develop approaches that lean on a combination of reinforcement and imitation learning to effectively solve a task of almost this complexity with a very limited amount of data and experience available to the agent. And so, unfortunately, I won't have time to show you the video here in the talk, but if you head over to mineral.io/competition, you can see a video of last year's winning agent, which is able to very effectively mine resources, construct tools, and it gets very, very close to actually getting that diamond. So we have all hopes that this challenge will be completed in this year's iteration. But now the key limitation of these types of approaches is that for each task, for each kind of scenario, current reinforcement learning and imitation learning approaches will have to be trained specifically to those tasks. So the limitation is here that once trained, they cannot rapidly adapt to new tasks or, for example, players or collaborators, as we set out as our next frontier. The approach that I want to talk about today is one that I was very proud to collaborate on with my amazing collaborators at Oxford University that you see here in the slide. And together we developed a new approach, which is called VARIBAD, which stands for Variational Deep Reinforcement Learning. The key idea in this approach is that we develop an approach that can learn to learn. So for example, if you imagine an environment where it's quite easy to simulate a wide variety of settings, you essentially pre-train an agent or an algorithm so that it learns to learn and at deployment to very, very rapidly adapt to a new situation that it has not seen before. Just to give you a motivating example, I'm showing a kind of toyish environment to illustrate this particular challenge over here on the slide. So you see here a kind of research environment that we use to test our approach, which is a grid world where you see the starting position of the agent over here. And in every so often, there is a switch in the goal position in terms of the goal that the agent needs to reach. So here, hidden to the agent, you can see the currently selected goal position, but in principle, every couple of rounds, the goal would reset and the agent has no idea where the goal is and what task it needs to solve in the new iteration. So you see this as an illustration to really rapidly adapt to a new task at hand in line with the variability of the agent about the environment that it expects to interact with. Now, what we're aiming for here in terms of the solution concept is to train agents that learn what we call base optimal behavior. Base optimal behavior means that an agent would maintain a belief over its current task. So in this example, it would maintain a belief over possible goal positions. And you can see here, if it has already visited some potential goal positions, its belief that the goal is there will be reduced. And so it will now focus its exploration on these remaining possible goal locations. An agent that is base optimal shows the optimal behavior, assuming that its current belief over the environment is correct. And so we can contrast base optimal behavior with a previous state-of-the-art approach called posterior sampling, where instead of learning base optimal behavior, the agent at each time step samples a possible belief and then acts optimally according to the sampled belief. And this can lead to so-called dithering, where in each step, the agent may switch between possible goal locations without really learning how to explore the environment systematically and actually act base optimally. In contrast, we can see that the approach that we propose is actually learning this systematic exploration. So it systematically seeks out goal locations that it has never visited before, very effectively sweeping the space of potential goals. And we can also see this in terms of quantitative results. Mapped out here on this plot is the theoretically possible base optimal behavior, and we can see that our proposed approach is very, very close to actually achieving this base optimal behavior, meaning that it has learned to systematically seek out information in order to complete a task. Now, how did we actually do this? The key idea in our approach is that we aim to flexibly learn base optimal behavior so that the agent can rapidly adapt online with minimal assumptions. And the approach we propose has three main components. First, there is an encoder which learns to embed trajectories, so state action reward tuples that the agent has encountered before. And it encodes this in what we call a belief, which is a variational representation, a belief over the kinds of tasks that the agent might currently be in. The second component is a decoder, and it learns to decode the belief, the embedding, in order to predict what will happen in the future. And so the key insight here is that this decoder needs minimal assumptions that every reinforcement learning agent makes in order to predict the next state and the next reward function. So it's essentially learning the dynamics of the environment that the agent is interacting with. And because it learns to decode this variational representation, this belief that we post, it is able to decode all the different variants in which the environment may transition in the future. The final component is our policy, and this is actually a model-free policy trained using standard reinforcement learning, standard deep reinforcement learning approaches. But the key difference is that we condition this policy on the belief that the encoder has learned to encode. And so this means that the policy can learn how to optimally trade off, for example, how to explore the environment with directly using the information that it already has, the so-called exploration-exploitation trade-off, in line with the belief and the uncertainty over its belief given by the current belief representation. On this slide, I'm showing some of the results we were able to achieve using this approach. And these are obtained in the so-called Mujoku task, which is a commonly used physics simulator. You can see here our comparison with standard baseline approaches. And in particularly, we see in yellow that our approach behaves near optimally in line with Oracle performance. I can also show qualitative results here, and you will be able to see that the agent briefly moves in the wrong direction before figuring out the actual task and then moving backwards as intended in this particular task. So you can see that it is indeed able to very, very rapidly adapt to this task. So in this talk, I introduced one particularly exciting new frontier of machine learning, namely the task of rapidly adapting to new tasks and players, a challenge that is particularly important in video game applications that we are currently working on. We introduced a powerful new approach called VaryBad, which flexibly learns base optimal behavior in a wide range of settings. Next, our team will focus on applying this and similar approaches to gaming and other applications. And if you would like to learn more, I invite you to visit our website at aka.ms/gameintelligence in order to learn more about our research and the exciting applications that we're envisioning. Thank you so much for your attention.
Hi, thanks for tuning in. So this talk is about generalization and exploration in reinforcement learning. Let's start off by just recapping what reinforcement learning is. So reinforcement learning is a sequential decision-making setting in which an agent interacts with an environment to optimize some sort of long-term reward function. And in the modern era, we've seen quite a flurry of interest in applying reinforcement learning methods to complex settings like gaming, robotics, and dialogue. So in all of these settings, the agent operates on raw sensory information, something that I'll refer to as rich observations, and has to accomplish these long-term planning sort of tasks. Now, we've seen quite a bit of success in the context of gaming, but somewhat less so in robotics and dialogue. And the main reason here is that the modern reinforcement learning methods are highly sample inefficient. So they can only be applied to settings where we have a high fidelity simulator, like gaming, where sample inefficiency is a bit less of a concern. Now, since we're talking about sample efficiency, I think this is quite an opportunity for theoreticians because we can think about designing algorithms that are provably sample efficient. And so that's our goal. We're going to design provably efficient sequential decision-making methods that scale to these complex domains. And before getting into the technical part of the talk, I just want to pause for a moment and think about why this problem is difficult. So these reinforcement learning methods must sort of demonstrate three core capabilities. These are exploration, credit assignment, and generalization. So exploration is all about planning to navigate the environment to collect the information you need to learn further. Credit assignment is about this causal question of understanding what decisions that you made in perhaps a long sequence of decisions are relevant for the outcome that you are observing right now. And generalization, this is really the purview of supervised learning. So this is about using information you've seen in the past to make good decisions in a situation you've never been in before. So the research community has been thinking about this problem for some time. And one way to design algorithms that achieve all three of these goals is to first start by designing algorithms that achieve 2 of 3. And we've actually done this with quite some success. So on the left-hand side, addressing exploration and credit assignment, we have these methods called tabular reinforcement learning methods. We also have policy search that addresses the other two, and contextual bandits that addresses exploration and generalization. Let me just take a moment to describe these tabular methods because it'll be relevant. So tabular methods are algorithms that do exploration and credit assignment, but not generalization. And they work in these settings where the agent does not operate on rich observations. Instead, the agent operates on a discrete finite state space with a finite action space. And what you can show here is that there exist algorithms that in polynomial time and with a polynomial amount of experience provably find near optimal policies in these problems with finite state and action spaces. And so these three sorts of lines of work are relatively mature, and these things are deployed in production today. But when we talk about getting algorithms for all three, this area is still relatively underdeveloped. And just to drive this point home, let's consider this very difficult exploration problem. We call this the diabolical combination lock. So here the agent starts uniformly in 2 states. From these 2 states, there's one good action that transits you down the good chain, so you end up uniformly in the next 2 good states, and 9 other actions transit you to the bad state. This repeats for some time, for 100 time steps, and if at the end of if at time 100 you're in the good state and you take the good action, you accumulate high reward. On the other hand, if you ever transit to the bad state, you accumulate some low reward. So this is the environment, and it exhibits many challenging aspects for reinforcement learning algorithms. First of all, there's a long horizon. You have to make 100 actions exactly correctly. There's stochastic dynamics, which preclude the use of open loop policies. You really have to look at the state you're in before you choose which action to take. There's also anti-shaped and sparse reward. So this is actually encouraging the agent to go into the bad chain until it realizes that there's the good chain has some reward that can be accumulated. On the other hand, so far, there's only 300 states. There's only 10 actions per state. So this is still in the purview of these tabular methods. It's a finite state space, finite action space. We can actually run these algorithms that do solve this problem. And really, there's no generalization required here. So I'm going to bake in some generalization. And the way I'm going to do this is I'm going to, instead of showing the agent the discrete state, I'm going to show the agent some high-dimensional signal, maybe an image that's generated from the latent state. And every time the agent is in a state, it's going to see a slightly different image. Perhaps there's some noise in the process. And OK, so now the agent really does have to generalize. And this is sort of the environment that we're thinking about. And I'll show you this in a moment, but these algorithms that we know from the empirical successes really do fail quite spectacularly here. OK, so we want to solve problems like this. And thinking about this problem a bit further, a natural sort of solution strategy emerges. And this is via representation learning. So that problem, there's this, the agent sees this high-dimensional signal. On the other hand, the dynamics are governed by this discrete state space. And I told you that we actually have algorithms that can solve this problem if they knew the state a priori. OK, so maybe a natural strategy is to learn how to decode the latent state from the observations. And this is a form of representation learning because the latent states are a representation of the environment. And that's the kind of algorithms that we're going to develop here. And to formalize this kind of approach, we need to think about a model in which the latent states are actually governing the dynamics. And so this is what the block MDP is doing. So here it's a rich observation problem with a discrete latent state space. The agent operates directly on the observations. And here's how it goes. So at any time the agent is in a state, you can think about it as the position of the agent in some grid world. The agent does not observe this position. Instead, the agent observes some high-dimensional input, for example, an image from a first-person camera. The agent takes an action, transits to the next state, and so it repeats. And so we want to design algorithms that provably explore and find near-optimal policies for these block MDPs. Okay, the key challenge here is actually that the latent state is never observed. If it were observed, we could just do supervised learning, learn a representation of the world, and apply a tabular method. But the latent states are not observed. So what can we do? So borrowing some inspiration from the empirical literature, we looked at a couple approaches. So one is unsupervised learning. A popular approach is to use an autoencoder. Another one is just model-based learning. You just learn the whole dynamics of the world, which actually pass through this latent, discrete latent state space. And another approach is based on auxiliary supervision. So here, maybe you would train a predictor to predict the action that the agent took on the basis of the observation. So we looked at these a little bit, and in the paper, we actually have some failure cases for a lot of these approaches, and I'll refer you to the paper for details on that. I will tell you what we do. So we use a form of auxiliary supervision, and this is what we call contrastive learning. So here's how it works. The basic idea is for contrastive learning, you're trying to predict real events that could happen in the environment from fake ones. You're trying to distinguish between real and fake events. And the way we do this is we collect triples by rolling into some observation with a policy, taking an action, and seeing a new observation. We do this again. So we have this x1, a1, x1 prime, x2, a2, x2 prime. Those are real events that could happen in the world, real transition triples. And then we're going to splice these two things together. So we're going to create a negative example, which is x1, a1, x2 prime. And this is an event that's very unlikely to happen in the world. And we train a classifier to distinguish between these two things. And somehow this classifier, you can think about it, it recovers the dynamics of the process. And because the dynamics go through this discrete bottleneck, this contrastive learning problem also sort of recovers the latent states. And so we use this contrastive learning problem in an algorithm that we call Homer. And what we can prove is that this algorithm covers the states and finds a near optimal policy with the sample complexity that scales polynomially with all the relevant quantities, but it's completely independent of the size of the observation space. So this really can be used to scale to rich observations. The algorithm also runs in polynomial time whenever you can solve this contrastive learning problem in a tractable manner. So let's return to this hard exploration problem. So we ran a bunch of methods, and some from the empirical literature and, of course, Homer. And here what I'm showing you is the visitation frequencies of these algorithms along these three chains when I run the methods for 1 million episodes. So PPO, which is this very popular policy search method, it only makes it to, time step 5. And then it sort of always falls into the bad chain and never achieves near optimal reward. RND, this is the random network distillation strategy, which is an exploration strategy. This is pretty good, but somehow has quite high variance. So we could not get it to move past time step 28. And I wouldn't be showing you this slide if Homer did not succeed, but we found that Homer actually has quite low variance. It consistently explores the whole environment, recovers the latent model, and achieves near optimal reward. So that's all I want to say about Homer. Let me just switch gears and tell you about a richer model. So this is the low rank MDP. So here you have this transition operator, this thing that governs the distribution of the next state, next observation x prime, given the current observation x and the current action a. And we're going to assume that this transition operator admits a low rank factorization, where each entry of this T matrix can be written as the inner product between a latent representation phi of xa and another representation mu of x prime. And I'm not going to make any assumptions about the size of the observation space. So this matrix on the left could be arbitrarily large, but I am going to assume that the embedding dimension, this dimensionality of this phi vector, is relatively small. That's the embedding dimension D. So I really like this model, and just to motivate it a little bit more, there's 3 remarks I want to make. So first of all, the latent, this low rank MDP actually generalizes block MDPs, but is actually substantially more general. So we can show that there are low rank MDPs with embedding dimension 2 that cannot be written as any non-trivial block MDP. The second remark is that actually learning these low rank MDPs is tractable whenever when someone a priori tells you the latent representation phi. This is this remarkable paper by Jin et al. From last year. And so this sort of gives us hope that if we can learn the phi, then we can sort of apply this previous algorithm to explore and do these planning and reward maximization. The last remark is actually that this setting is tractable statistically, even when the latent representation is not known a priori. But unfortunately, the algorithm from this paper is computationally inefficient. So the goal here is to develop a computationally and statistically tractable algorithm for this more general model. And the way we're going to do it is by trying to learn the representation phi, even though it's not given to us a priori. Okay, in the interest of time, I'm just going to give you a really whirlwind tour of what the algorithm is. The algorithm is called Flambe. It stands for feature learning and model-based exploration. And it's a model-based approach. It's very simple at the high level. It just alternates between fitting the dynamics and model-based planning. And the way we learn the dynamics is we learn a low-rank MDP model via maximum likelihood estimation with function approximation. So maybe we use a neural network to maximize the log probability of the transitions, and we architect the neural network so it has this low-rank factorization at the last layer. And then, so that the neural network will actually give us a learned feature map, hat phi, and we plan to explore using this algorithm of Jin et al. And our learned features. So that's like the high level. The details are fairly complicated, but I do want to tell you what we proved. So we proved that Flambe learns a low-rank MDP model M hat that universally approximates the true model in the sense that for any policy, any reward function, the value for that policy and that reward in the model is about the same as the value for that policy and that reward in the true world up to an error tolerance epsilon. And this happens, we can do this with a sample complexity that scales polynomially in all the parameters, independent of the observation space, and with the statistical complexity of the class of functions we're using for the maximum likelihood estimation. As before, Flambe can run in polynomial time, assuming we can sample from the models and solve MLE problems. And just to mention about the representation learning aspect of this, we also prove that for any reward function, the near optimal policy is linear in our learned features phi. So the features that we get are actually a good representation in the sense that they allow us to approximate the things we care about. So that's all I wanted to say. Just to wrap up. So the conceptual approach here is to decouple the dynamics assumptions from the observations. And this yields sort of tractable reinforcement learning settings where we still have to use nonlinear function approximation. And this sort of allows us to scale up to rich observations in a provably efficient manner. In recent work, we've been able to show that we can use this approach effectively to learn environments like block MDPs and low-rank MDPs. And the way we're doing this is using the strategy of representation learning. So in some sense, I feel representation learning provably enables generalization and exploration in reinforcement learning. With that, let me just thank my collaborators, Alec, Michael, Sham, John, Dipendra, and Wen, and thank you for listening.
Hello, I'm Asli Celikyilmaz. I'm a researcher at MSR AI, Deep Learning Research Team. Part of my research is to focus on learning or controlling discourse in long text generation. In this talk, I will show you our recent work on controlling discourse via the use of explicit memory in decoding. Text generation is one of the most important topics in NLP. We can build models like machine translation, which is a text generation system, and can encode the utterance of a speaker and translate it into another language instantly, perhaps to many languages instantly. Or you can build systems that can take multiple documents and generate short summaries that contain important and organized aspects, salient points in order. We can ask a system to summarize a multi-party meeting for us. There are several other tasks that I'm listing here that require automatic text generation system. So in essence, we need the text generation systems for several reasons. Because there's an abundance of information like meetings, emails, online search results, etc. If summarized well, they can help improve the efficiency. Also, AI robots can converse with humans and help speed up the learning for them. They can help improve productivity as well. For instance, online shops require large quantities of product descriptions, which AI systems can actually generate summaries for. Before I move on, I would like to mention a very recent talk by Josh Tenenbaum at ACL 2020. In his talk, he defined 3 different ways of teaching meaning for AI agents. The first one started with statistical language models. Another one was to building models that try to ground meaning in perception and action. And the third one was semantic parsing. which supports like logical reasoning and thinking. My talk is about building statistical language models that can teach machines write text like humans. So I'll start with talking about one of the recent methods we proposed to control the discourse with explicit memory in language models. I will then conclude, talk about some new open research questions for better text generation. I would like to start by talking about language models first, since text generation is a type of language modeling problem. Language models assign probabilities to sequences. Typically, they express this probability via the chain rule that I'm showing here as the product of probabilities of each word conditioned on that word's antecedents. So why do we actually need this probability? Well, in speech recognition, a phrase like "I saw a when" is much more likely than the phrase like "eyes of fn." Or in speech recognition, or like, sorry, spelling correction, we see a phrase like 15 minuets. That's more likely to be a mistake than minutes. So a language model can actually quantify this true sentence probabilities, which plays a role in several other tasks like machine translation, summarization, question answering. So they're really everywhere. So in text generation applications, mostly, we use this language model and condition it with a prompt. And prompts can come in many forms. Here's an example of a constraint generation problem. The goal here is to generate a paragraph or a multi-sentence text that describes the people, the setting, attributes, animals, mood, etc. In blue, you notice that I'm showing core references, relational information, lots of prepositions like behind, under, etc. So while being extremely powerful, these language models can actually suffer from a number of issues. For example, if you tune your language model with an encoder-decoder architecture and keep the decoder as an RNN-based language model, you might end up with text like this I'm showing on the right. Some of the issues you can see are repeated n-grams, the model contradicts itself, the text is not really specific or sensical. So there are fundamental issues, not just with RNN language models, but in training of the text generation models in general. Some of the issues related to the text generation are, for instance, exposure bias, which is related to the discrepancy between the training and the test time, because at training time, the model is conditioned on its ground truth, while at test time is conditioned on its own generations. There are other issues related to the compounding errors, like caused by this label bias problem that I'm showing here. It's related to the fact that the previous bad decisions can actually hugely affect the current decisions, which cause small errors to accumulate. Also, large vocabularies can cause softmax bottleneck issues, in which the learned latent representations is mapped to a multinomial probability distribution over the vocabulary, which is usually very large. Last but not least, we train the generation models using a surrogate objective function, which is a cross entropy, without considering end goal. But then if you consider the end goal and add training data with things like reward-based auxiliary losses, it may also additionally cause inconsistencies. One might say that most of these issues actually, to a degree, resolve with today's more sophisticated as well as complicated neural language models. So let's look at some of them. So this picture actually summarizes several novel language model methods that I proposed recently. So the basic idea of these methods is to train a language model on a massive amount of unlabeled data, and then use the internal representations of the language model on subsequent end tasks. This was a form of transfer learning. Our expectation is that these highly advanced today's language models should actually result in significantly more coherent and realistic simulated content. So let's see some examples. So the context I'm showing here is from a GPT-2 paper from 2018. It's about someone making a chocolate cake, explaining how that is made. It's a bit different than a recipe, actually. So if you give this to a GPT-2, it decides that the text needs a proper recipe and generates one almost perfectly. So it's actually an amazing performance. But most often than not, we see some issues with these type of generations. Again, using the same recipe with a different sampling strategy, we immediately notice things like incoherence in text, for instance, like this. I'm showing here in bold. But still, these are not that easy to differentiate between how like a human written text. So what is happening here? Well, if we look at the core of the reasons, we see that we're trying to model the meaning of a word by looking at its context. For instance, at the top, as a decoding from left to right, which is a GPT-2 language model, down is a birth-style language model. So we train these generic language models with no explicit planning, with no information about the narrative flow, topic structure, or any other additional information, and we expect that they should do well at writing long text or stories. So we claim that by just learning, by predicting the next token, given the context, is not enough to generate multi-paragraph long text. So this brings us to the discussion of how to control the long text generation for better narrative experience. So there are many ways we can control the language models for better generation. Here I will discuss only one of the ways, which is controlling via discourse. So our goal is to teach the language models about how to plan before and during the writing by mimicking the way the humans write stories. Specifically, humans write down these plot elements or key events that they want to occur in a story when they're writing a long-form story. Our goal is, starting with these outlines, teach a machine to order these outline story elements, which are plot elements, and then write a consistent story out of them. That makes actually sense. This is the work that I'm going to be explaining. So we have 3 goals. We would like to generate a fluent multi-paragraph stories. We will start with a large pre-trained language model like GPT. We also want to keep track of the various plot elements in an external memory state and make sure that they are being combined in a way that seems possible. Lastly, we want the generated stories to have a good narrative flow. We're going to introduce various discourse-based features to allow us to generate more discourseful stories. Okay, so in order to generate more coherent paragraphs that follows the context of the previous paragraph better, we're going to take the outline that we're using as input. We're going to send it to a GPT-2 to generate a single paragraph. And we're going to generate a paragraph. Because this is a supervised structurally conditioned learning task, is going to learn to generate a paragraph given these unordered outline points. Now, we hypothesize that different portions of the narrative are written stylistically differently. So for instance, an introduction paragraph or a setting paragraph of a story should actually slightly be different than a body paragraph or a concluding paragraph. So what we do is we introduce these discourse markers, like I meaning introduction, into the GPT-2 as a prior information. So we can then continue this paragraph generation as like a incremental generation task. After we generate each paragraph, we continue generating other paragraphs using the same outlines. In order to control the narrative flow between paragraphs, we are going to introduce the next paragraph representation and send it to the next paragraph generation as an input. We're going to also adjust this discourse marker because we were generating an introduction and now it's going to be a body paragraph, which is following the introduction paragraph. So notice how we keep changing the checklist markers on the left of the outline every time we generate a new paragraph. So the idea here is to keep track of various plot elements such as events, objects, relations that are already mentioned in the paragraph. So we generate the next paragraph given these aspects that we didn't get to mention before. This is a way of dynamic plot state tracking. And the way we implement is through defining an explicit memory. So we want to have a memory unit that is keeping track of all the plot elements that we're discussing. We're going to have an explicit memory matrix such as this, which is going to be split into 2. And they will carry different information. So the first piece is initialized with all the different plot elements coming from the outline we're using as input. And the second part of the memory is going to keep track of the global document state by keeping track of the latent topics that have been discussed so far. Now, using this memory matrix, we actually alter the GPT transformer blocks to include this memory component as an additional attention mechanism in which the decoder not only attends the previous tokens, but also the memory component that keeps updated every time we generate a new paragraph. Also, these components injected into GPT architecture now constitutes our model, which is called the plot machines. Now down to the experiment to see how our language model differs from other language models. Before I do, I'm showing here a neural architecture for those of you who are interested in, but I'm not going to go into details of that. So we compare our model to several baselines, one of which is a very strong controllable baseline, which is Grover. It's one of the large language models, which is another controllable generation in which the control is based on the attributes, such as these entities related to the context that is provided at the prompt time. So for the experiments, we conducted a new outline labeled document dataset. This dataset consists of articles such as Wikipedia articles or newswire articles or stories, and corresponding list of key points. And we fine-tune our models, our model and the baseline models in a supervised way with these outlines as input and the documents as output. Instead of showing accuracy numbers, I want to show you a somewhat more reliable way of evaluating text generation, which is the human evaluation. We conducted human evaluations to benchmark the model's outline usage, narrative flow, ordering of aspects. And I'm showing here a comparison with Grover, which resulted in the outline condition generation, and that the plot machines can actually learn to keep track of the context better, and it yields stories that have higher narrative flow compared to the Grover. And this was like evaluated with humans. All right, to conclude, I presented an outline condition story generation, which is a new task for generating stories for outlines, keeping which represent the key point elements. We call this plot machines, which generated paragraphs using higher level discourse structures and dynamic plot memories to keep track of the outline and the story. And our quantitative experiments and qualitative experiments show that these plot machines are effective in composing tighter narratives, which are like focused narratives based on these outlines, compared to the competitive baselines. We also released our code if you're interested in trying it out. Lastly, I would like to mention a few key points and future directions we should consider for long text generation. Firstly, text generation systems need to be able to perform common sense reasoning, specifically regarding characters' goal and their associated actions. And we need a better way to incorporate common sense knowledge graph into long text generation for better text, human-looking text. Secondly, building accurate language models that capture meaningful long-term dependencies is actually a core challenge in natural language processing. So we need to be able to learn well-calibrated language models and track and manage the content that is conveyed in there through better evaluation metrics and even shared tasks. We should also look at the way we do decoding and find better ways to mimic human generation process. Lastly, I want to say a few things about evaluation. Training a powerful language model actually relies on evaluation metrics that can measure the model quality from different perspectives. For instance, it's very important to build evaluation methods that can determine whether a text is generated by human or a machine to prevent any potential harm. Also, to me, it's concerning that neural language models can generate open-ended texts that are fluent, but not grounded in any real-world knowledge or facts, such as fake news. So we should be investigating this in the future. We have a new evaluation paper out there. It's a survey paper. And I would like to close by self-advertising. So I'd like to invite everyone to join our tutorial at EMNLP this year with my collaborators, in which we're going to be discussing more about these text generation and evaluation and several issues. Thank you.
Let's proceed right now with QA for the talks by Katja and Akshay. And we have a few questions, one question from me and several from the audience. So let me start with an initial question for Katja and Akshay. So you both presented some really impressive new theoretical analyses of RL systems that use some form of abstraction to identify related states that are used to support a more efficient exploration and adaptation. So Akshay, you used kinematic state abstractions, and Katja, you used meta learning over simulated states to share knowledge from related tasks. You described some really impressive initial results of these systems. And, but I also know that you've both previously worked on much more complex real world scenarios. And so my question for the two of you is, what advances will it take to move Very Bad and Homer/Flambe to get to some of the broader complexities that we see in real world scenarios?
Oops. Maybe I can start with a take on this. I think this is a fantastic question. And Sue, as you know my work, I'm really passionate about solving hard research challenges with in mind really getting to the point where we can enable new real-world applications. And I really see Very Bad as a kind of case that really makes this point. We started from this general concept of base optimal behavior and then tried to rethink how we can use domain expertise about a certain domain in order to utilize simulations and training that can be done in simulations before a system is deployed and actually needs to very rapidly adapt to a real world situation. So if you imagine kind of a scenario of, let's say, patient flow optimization in a hospital, we can imagine building very complex simulations where we can incorporate a huge amount of expertise that already exists about those settings with all the different kind of variations that such a system might encounter in a real world environment. We would then pre-train the system in simulation using as much data and compute as necessary, and also with the ability to test the system and really understand whether it's learned appropriate decision making. And then at deployment, the system would be expected to generalize as long as the kinds of parameters of the real world system have been covered in the simulation. So this would give us a setting to utilize massive simulations, but then at runtime, very, very rapidly adapt and optimally adapt to the context at hand. What we proved out in the system, or in Very Bad, is that we can use a very flexible encoder-decoder architecture that uses latest advances in deep learning to learn a representation of how different settings might be related to each other in a latent state. And with this kind of work, we remove important bottlenecks of kind of using very flexible state-of-the-art models for doing this. So we are very excited to see how far this can already be pushed into real-world applications, and we're actually examining at the moment where we can take a next step to prove out how far this can be taken along this road. We don't know yet what challenges will come up, but I think that is a really exciting journey.
Thanks,
Katja. Yeah, Susan, this is a great question. And yeah, the way I kind of think about Homer and Flambe are kind of very like blue sky kind of approach. And there's, I think, a lot of steps that we need to take before these things are like something we can actually deploy, let's say in like production. One thing that I'm quite interested in doing in the near future is actually starting to sort of incorporate more of the ideas from the empirical literature. So when we're working on these projects, we're definitely taking more of a theory first kind of approach, where we start with like basic foundations of learning theory and trying to apply them to RL settings. And I think to make these things even like something we can implement and run on the standard deep RL benchmarks, I think it's going to be really important to understand what are the empirical approaches that are working effectively there, and how can we sort of like close the gap between what we prove and what is kind of already working reasonably well in practice. Mm-hmm. But I think actually, if you want to move to, let's say, like more high stakes, much more data limited settings that might be relevant for various production applications like robotics and these kind of things, I think there's many other issues that are also kind of relevant. So one of my pet peeve issues that kind of keeps me up at night is the fact that we actually don't know how to do cross-validation when an agent is making decisions about data collection. And this is a huge problem, because cross-validation, I feel, is like some bread and butter procedure that everyone uses when they use machine learning. And we don't know how to do it very effectively, even for contextual bandits, which is a much, much easier problem than the things we're talking about in here. So I think if we actually want to get these things to be productizable or whatever, we do have to think about how can we do some of these other things that are very important for getting machine learning into production.
Mm-hmm. Okay. Thanks. Let me follow up on that a little bit, Akshay. The work that you've done on Homer and Flambe do this beautiful theoretical analysis of and prove guarantees when you have a very simple assumption of only low rank MDPs. And so you really are starting to tackle fundamental issues, I think, in representation learning in RL, assuming that there's only a low rank state transition matrix. In practice, can you imagine adding additional structural assumptions for particular applications? Have others tried that in the literature?
Yeah, so maybe since the audio video is a little bit strange, let me just summarize briefly what we prove about Flambe. Yeah. So we're considering a MDP model where the transition dynamics admits a low rank factorization, but we make no assumptions about the size of the state space. We only assume that the rank of the transition matrix is relatively small. And what we prove is that you can do this model-based function approximation-based algorithm that does strategic exploration while learning a dynamics model that admits the low rank factorization and gets a sample complexity that scales independently of the size of the state space. And this is sort of, and let me just add briefly, the algorithm also sort of identifies a good representation, which is sort of the factors of the dynamics model. And this lets you do efficient reinforcement learning with linear function approximation afterwards. Now, to get back to your question, I haven't seen too much. I'm not the most familiar with empirical literature, so on the theory side, I have not seen too much, but I think it is a super important thing that we need to think about. So one model that I think is, from a complexity standpoint, quite difficult, but from a practical standpoint, quite important, is like a factored MDP model, where there are many sort of objects in the world and they're evolving relatively independently. And because the evolution is independent, the complexity of the system is actually quite low. If all these factors were interacting all over the place, this would be a very, very hard thing to learn and to model. But when you have these factors evolving independently, it's something that seems relatively simple, right? And that, I feel, is quite a good fit for the real world. Yep. Right? Most people go about their daily lives and just bump into a few other people and so on. And that's a model that other folks in the MSR NYC lab are working on, and how to sort of learn a representation that admits sort of a independent factors kind of decomposition. And I'm also wondering if somehow the low rank structure can be thought of as, maybe can be generalized to like tensor structures, which also can maybe capture some of these many factors evolving kind of independently. So I think this one is quite an important one. I have not seen much theory work on it, but I think if we want to sort of push to capture very complex systems, this is something that we might want to try to think about.
Okay, thanks, Akshay. I think that's first of all, I think it's a fabulous result, and you're right that there is a lot of structure in the world, and you should be able to capitalize on a lot of that. So I hear from our crack crew in the back that we are ready to resume the live feed. So let's go back to that, and then we can come back as a group of 4 and take questions from, again, me and the audience. So thank you, Akshay and Katja, for starting the Q&A early.
Hi, everybody. I'm Dan Klein, and today I'm going to be talking about the semantic machine's approach to conversational artificial intelligence. In particular, I'm going to be talking about task-oriented dialogues, which are designed to be trained from data and which are grounded in services in the real world. All of this work is joint with the amazing people at Semantic Machines, shown here in a photograph from back when such photographs could be taken. Language is so important because it's a universal interface, not just in the sense that people already know it, but in the sense that it promises to unlock the entire universe of capabilities in the technological ecosystem that's around us. Let me show you what I mean. Right now, we live in an ecosystem with tons of services and capabilities that surround us in tons of devices. However, the kinds of things that we do with them are often easier said than done. For example, if I'm using my calendar, I might want to know, when are Megan and I both free? Now, I can figure this out in my calendar, but it might take a lot of work, and it takes barely any time at all to say it. Similarly, If I'm preparing slides, I might want to delete the footer of this document. It's easy to say, but it might be hard to do. In this case, it might be hard to do because it's a piece of functionality that hasn't made it to the short list of what's exposed in the GUI. As another example, I might want to know what the weather's going to be like during my morning run. Now, in this case, I can get this done, but it involves multiple steps and I have to do the orchestration. And as a final example, maybe I want to set the photos from yesterday's party as my TV screensaver. It's really easy to say, but it might take me a long time to do. What we really want is for the computer to do this orchestration for us. So what are the standard approaches to language interfaces and how do they solve these problems? Well, the standard approach is about intents and slots, and let me show you how it works. If I say something like turn on the lights, the idea is the world has been sliced up into a bunch of domains, like calendaring or home automation, and in each of those domains, there is a list of functionality that is supported. Each square here represents something the system has been programmed by hand to do. In response to the user utterance, we pick the one that's appropriate, for example, maybe the one that turns on the lights, and this choice is done using machine learning. It's basically classification, and this can be extended. For example, if I say set a timer for 5 minutes, I can use machine learning to classify that to the set a timer function. But I can also extract out the 5 minutes as an argument to that function. So how far can we push this? Well, what if the user says something like, what time am I getting coffee with Megan? We could probably just about make this work, though it might get a little creaky. But let's imagine that we found the appropriate functionality and we answered 12:30 p.m. But now what happens when the user asks a follow-up question, like how long will it take to get there? Well, now we're in a little bit of trouble. Because 1, this is a contextual question, where is there? And 2, it's not really just about calendaring anymore, because this connects up to multiple different services in multiple different domains. And that doesn't really fit the paradigm. So what's the semantic machine's view? Well, instead of viewing the world as being composed of a bunch of pre-bundled units of functionality, instead we imagine there's a whole space of things the system might be able to do. And in response to an utterance from the user in a context, instead of picking a pre-bundled unit, we're going to synthesize a new program which combines multiple actions dynamically. This program we synthesize can hit multiple backend services and isn't confined to a single domain. In this talk, I'm going to focus on 5 key ideas of our approach. The first is that dialogues are actually programs, and this is going to involve techniques of program synthesis. The second is that complex tasks are actually built up out of simpler ones, and this is going to involve compositionality. The third is that meanings are going to inherently depend on context, and we're going to handle this with techniques of metacomputation. Fourth, things will go wrong, and so I'll talk about how we approach this through a lens of exception handling. Finally, we think systems should tell the truth, and that's going to require new techniques of dynamic generation, where we take as a primary focus the truth of the system and not just its fluency. So now let me tell you what I mean when I say dialogues are really programs and what this has to do with program synthesis. Even for a simple utterance like turn on the lights, we could view this as synthesizing a program. Here the program would be something simple like calling the function turn on lights. If the user says set a timer for 5 minutes, we could see this as again calling a function set timer, but now with an argument which is extracted from the input. This is about what the normal standard setup is designed to handle in terms of intents and slots. This can be pushed a little bit. So for example, if I say, what time am I getting coffee with Megan? You could imagine having a time of calendar event by title and attendee in which you pass the title and the attendee. This is where it gets a little bit creaky, but this can be made to work. And in fact, in standardly deployed systems, you do often see things just like this to push just a little bit further into the tail. The problem is you're trying to handle a combinatorial problem by enumeration. So what could we do instead? Well, instead of synthesizing this single function call in response to what time am I getting coffee with Megan, I could instead break it up into a sequence of simpler steps. First, I could find a person whose name is like Megan. Then I could search for an event with a title like coffee that includes that person. And finally, I could describe its start time. Breaking this up into multiple pieces has several advantages. First of all, it's now easier to learn and easier to cover the long tail of combinatorial interactions between these atomic pieces. Secondly, the structure of the input language sometimes, but not always, provides a strong clue to the structure of the program itself. Once we frame dialogue as a program synthesis task, this gives us a nice treatment for compositional behavior, both inside a turn and across multiple turns. For example, within a turn, if somebody says something compositional like, "What's the temperature going to be for my coffee with Megan?" this causes a big problem for a classic system because the slots and fillers approach doesn't naturally synthesize or integrate across domains. However, here we can start out with the same program that finds that event, but instead of describing its start time, we keep on going once we found the event and do the computation needed to get a weather forecast for that event's time and place, and then finally describe the temperature. This lets the system answer the compositional query in a compositional way. Notice that the information flows from one part of the program to another via variables in the structure of the program. What happens in a multi-turn context? Well, if somebody says, "What time am I getting coffee with Megan?" and we synthesize the program to answer it, and the system gives a time, and then they follow up by saying, "What's the temperature going to be?" Well, again, we can simply handle this multi-turn interaction by continuing the program. Again, the flow between turns is now along the computation structure in a nice way that parallels what happens in the single turn compositional case. Behind all of this is actually a computation graph where each computation we do represents a node in the graph, and this graph is persistent and represents the context for future parts of the dialogue, as we'll see. When I say that information flows along a variable, what this actually means is a node in that computation graph is shared between the older computation and the computations that continue it. Another major limitation of standard approaches is that meanings depend on context. We handle this through metacomputation. So for example, let's look at the case of reference. Maybe the user said, "What will the weather be like?" And it's easy enough to synthesize a little program that finds the weather forecast at here and now. However, what happens if we've just been talking about coffee with Megan at 12:30, and then the user says, "What will the weather be like?" Well, we could synthesize a program that finds the weather forecast at that event's location and time. What we do instead is unify them into a single analysis, which in both cases says, "Get me the weather forecast at the salient place and time." What this does is the computations appeal to a metacomputation, which involves place and time, which are now to be extracted from the compute graph in a dynamic way. Another big contextual challenge is revision. Let's say a user says, "Do I have many meetings today?" Here's a fragment that computes that. Now, what happens if the system says no, and the user says, "What about tomorrow?" Well, of course, we can synthesize a fragment which finds meetings tomorrow. But what about tomorrow might occur after asking about the weather. And now what about tomorrow needs a program that finds the weather tomorrow? Or what if it happens after "What's the weather going to be like during my third meeting today?" and you say, "What about tomorrow?" Let's see how metacomputation on the data flow graph can handle all of these in the same way. Let's say the user says, "Do I have any meetings today?" and we synthesize a program to find today's meetings. And then they say, "What about tomorrow?" Well, of course, we could just synthesize a program to find meetings tomorrow. But remember that the data flow is still around from the previous computation. And so what we're going to do is, rather than synthesizing a new program from scratch, instead we're going to synthesize a revision to the previous computation. It's going to look something like this. Whereas before, metacomputation found a value in the compute graph, now we're going to find a node in that graph itself. And then we're going to do a program transformation on that fragment to build a new compute graph, which we will then execute and describe its result. Now, what about tomorrow more or less means do the salient computation, except this time, do it with tomorrow substituted in for the salient date. Next, what happens when things inevitably go wrong? Here we have a representation for exception handling, which handles not only true errors, but actually quite a wide range of things that can happen in a dialogue. For example, let's say the user says, "Set up a meeting with Megan." And we synthesize a program to find a person like Megan and then to create an event with them. What could go wrong? Well, maybe the system finds more than one Megan, or maybe it finds no Megans, or maybe there's an API that has an error during this process. Or maybe you can't create a calendar event without a title, and so we get a missing slot error of some kind. In each of these cases, the program will not completely execute and will instead raise an exception. Let's imagine that there's more than one Megan that is salient. Well, in this case, a multiple matches found exception will come back into the system and will trigger a new round of program synthesis. This program synthesis will most likely be a revision of the previous program using metacomputation to transform it into something that, for example, asks for a clarification before continuing. This turns out to be very powerful, not just for handling true errors, but for elegantly handling a wide range of things that can modularly go wrong. Finally, I said programs should tell you the truth. Of course they should. In standard systems, the way this is accomplished is by having a list of templates of what the system can say. This doesn't scale to a case of contextual program synthesis, because if the system's constantly synthesizing new programs, it would constantly need new templates. So here's a sketch of how we let our generation be dynamic while keeping it grounded. When a user utterance comes in, we synthesize a program, and at the end of that program is a call to describe. Now, what we pass into describe is not just the value that we've computed, but rather the entire computation graph that led to that value. The generation module then uses the structure of the computation graph to formulate a response. Because the generation module has access to this computation graph, it's able to stay grounded to the values and computations inside and say something truthful, like in this case, it will be 74 degrees tomorrow at noon at Rosie's Cafe. Now, of course, it's also possible to say other truthful things, but hopefully we've avoided the system lying. For example, saying something like, it will be 99 degrees, when in fact it will not. In summary, all these techniques have been about reaching the long tail of things people can say, things they want to do, and context that they can ask for these things in. There is a long tail, and standard techniques focus on the head. Although standard techniques are actually quite good at lexical robustness, they've limited functionality by assuming that there is a fixed inventory of actions that have been manually curated. And they limit context by assuming that most of the time, little or no information is retained between turns. In contrast, the semantic machines approach is designed to reach that tail. It's based on compositional program synthesis so that we can build complex new programs out of simple building blocks. It uses metacomputation to manipulate past data flow graphs. It uses events and exceptions in order to react when things go wrong. And it has a dynamic but truthful generation system. Let me show you what this looks like when it's up and running. This is a demo of our system trained on data from multiple domains, like the ones seen in the talk today. Even though we didn't get into the predictive modeling here, the program synthesis, revision, and generation are all trained from that data. First, let's make sure that there's actually some program synthesis going on. So we'll ask it something that's much more specific than any hand-built intent or slot classifier would be able to handle. What's the weather going to be like 3 hours after I meet with Bree's manager next Tuesday? In order to deal with this query, the system has had to figure out which Bree we're talking about, who's her manager, find the event, and send that off to a weather service. Now let's show the program synthesis working across multiple turns of a dialogue using the compute graph reference machinery. When is my afternoon run? And the system looks that up. And now, what's the weather going to be like then? And here, that weather computation has used the information computed in the afternoon run query. Finally, let's look at a longer interaction that will show the metacomputation machinery doing reference and revision operations. Show me my day tomorrow. It starts off by fetching the day. Is Jason coming to the research group? and it's able to find that event and figure out whether Jason's coming. What about Diana? Invite her, please. Which her, invite her to what? That's been figured out using the reference machinery. Rename it to research and engineering discussion. Here the system's done multiple things. With program synthesis, it's very easy to do multiple things in a row. You just concatenate their programs. Okay, great. That's a quick tour of what the system can do. I've talked about a way to view conversational AI as a problem in truthful, compositional, and contextual program synthesis. There's a lot more to say here about the data, about the modeling, how this interacts with speech, and a whole bunch of other challenges that I won't have time to get into today. If you're interested in the details, a paper and a release of a data set are coming soon. And if you're interested in the system, then stay tuned for that as well. Thank you.
Thanks, everyone. And we are now ready to start the unified QA session. Before we do that, I know there were still some challenges with syncing of audio and video. So I want to start by asking Asli to quickly summarize some of the key takeaway messages for people, and we'll post the appropriately synced videos later today. So Asli?
Yeah, thank you, Susan. So I presented an outline condition story generation, and it's actually a new task for generating stories from outlines that represented key plot elements. And given an outline, for instance, as a set of phrases or engrams, which can describe key characters or events in a story, the task is to generate a coherent narrative that is consistent with the provided list of outlines. So this task is actually challenging because the input only provides just a sketch of the plot that we are asking the model to write. So because of this, the model actually needs to generate a story by weaving through all these key points and trying to find out which come, because we're not assuming that these key points are actually sorted. So it requires this model to keep track of these dynamic states of latent plot, conditioning on the input outline while generating the full story. So without going too much detail, I linked the paper that corresponds to the talk on my website and this page, and the code is also online. I've seen a question, and I'll put a link here as well. I just want to also mention that the model that we came up, or this approach, we just applied it on a story generation given this list of conditioned outlines, but we have been working on some other downstream tasks that this approach can be useful and efficient for other long generation tasks. Yeah.
Okay, great. Thanks, Asli, for the really cogent summary and for posting slide and code. I want to start with a question to Asli and Dan, who both had really exciting new results on data-driven generation. Asli in going from key points to a coherent long-form story, and Dan in going from questions to generating a sequence of programs through synthesis that compose actions, and then not so much about generating answers that a human consumed after that composition of actions, but still generating interesting summaries of the state of the world. A key component in these systems is really maintaining memory or context throughout the course of either a long sequence of text or a conversation. Asli and Dan, are there similarities and differences in the approaches you took, and what can you learn from each other?
Yeah, I think that's a great question. I think in some ways, my first reaction is that they're very complementary. So one of the things that I talked about but didn't really get into much detail is eventually the system does have to render text or speech that a human can understand. And at that point, you have this problem where you've done a computation and there's a lot of things you could say, but you need to make sure it's consistent and coherent with what you've done, and not just with what you've done, but with the dialogue so far. And I think that what Asli's is talking about in her work really dovetails very nicely with how you might go about doing that. There's always been a tension in generation between guaranteeing that something says exactly what you want, but not having much flexibility, versus these modern large-scale neural models that can say anything, but might lie to your face, even if they're attending to the true information. And the ability to make sure that when the system says that your package is coming on Friday, it's not actually coming on Thursday, but Friday is more common. These are going to involve techniques like what she was talking about. So I see these things as very, very compatible, and I think that's really some great work.
I just want to add, thank you, Dan. That was a great summary, and I do agree. I just want to add something on that is that, like, for instance, our models, unlike Dan's, is not doing any much factual consistency or conditioning on in a knowledge graph, for instance, or knows about common sense reasoning or things like people would think, oh, this is nonsense. We could, technically generate things that have some ethical issues or some bias, because the bias is based on what the pre-trained language model has learned. So I guess that's especially when generating longer text, we probably is what I'm currently these days I'm thinking is to focus on evaluation aspect and how to actually incorporate that into this generation models. And someone has already asked, like, if these models like GPT-3 can be deployed. If I do see these GPT-3s. I don't know. It depends on the infrastructure, and they're like huge models. They're potentially really useful because they're really good language models, and we do really need language models to complement our systems. And I really hope that we do. I don't know if Dan has any comment on that.
I totally agree. I mean, even in a system like ours, where we're so concerned with making sure that the system shows its work and tells you something that's true and tracking the provenance of that information, there's still all kinds of other decisions to make. Pragmatic decisions, you say more or less. We saw a little bit of that in the talk. There's decisions about being consistent from turn to turn and how you convey information. And I think these kinds of longer distance dependencies, which really are an important part of making a conversation natural and effective, I think are very important, and are the kinds of techniques that you're talking about are very, very applicable.
Mm-hmm. Yeah, thanks. You both raise this really interesting issue of going from generating sequences of words to larger constraints and pragmatics that govern how we generate text over throughout a conversation or over a long form story. So Asli, are there aspects of storytelling other than kind of the content or the outline that you showed that you think really need to be incorporated to do the the kind of long form story generation that you talked about?
There are very good question. Thank you, Susan. There are a lot of, I think there are work in RL, in these multiplayer games and others, also in dialogue as well, that you need to ground the generation in order to get what you really want from the system. For instance, you don't need to ground it, but in cases where you actually need the consistency or factual consistency, or like, for instance, in dialogue, you really want the system to know about some certain list of aspect or entities, or constrain it in such a way, then incorporating some sort of a knowledge graph structure into the generation would probably help generate more grounded, I'm going to use the same word here, but and also more consistent generation, especially for the longer text. But then this longer sequential learning also appears in not just for text, but also, like I said, in Katja and Akshay's systems as well. Right. Where, you know, the issue that I listed in my beginning of my talk, which you probably didn't get to listen well, but I hope you will later, is these, you know, labeled bias problem or compounding error. So if you do make an error, it's really hard to, you know, come back from that error. So how do you actually build your model? So, like, you know, we have these beam search algorithms. They're not that efficient, but I think, like, we need to think more about these longer term generations, and how do we actually maybe using reward-based systems or complementing the current generation text generation systems with those would probably a way to go, which are grounded in the knowledge graph. For instance, you can actually see if that reward can be aligned with the information that you provide, like the structural information.
So, Katja, Akshay, do you want to comment on that? Because I know a lot of your work is also, Katja, grounded in games, or Akshay right now in terms of the you know, the lower dimensional manifold that you use for representing state transitions.
Mm-hmm. Yeah, as Asli mentions, I think a lot of the kind of challenges that we're encountering are quite well aligned, and the kind of scenario that you mentioned there, thinking about grounding language in interaction with some real world environment, is something that's fascinating to me. It's not something that we've been able to really dig our teeth in so far, but I think we can learn a lot from Asli and Dan's work when we get to that point, and I'd love to work on that in the future.
Let me just add one quick comment. I think actually these things are also quite aligned on like a more technical level. So it feels like RL agents should also have attention and, you know, these like grounded knowledge graph type systems to help them reason about what decisions they should be making. And so there's like, I feel a real opportunity for maybe like all of us to actually like, I don't know, try to do something kind of
maybe briefly coming back to the
crazy,
discussion.
yeah.
That also really nicely aligns with the discussion of structure that came up earlier in the Q&A with Akshay in particular, right? So language provides some really interesting structure in terms of how we reason about the world. Connecting that to interaction and abstraction could be really, really promising.
Mm-hmm. Fabulous. We're nearing the end of the session. I want to give you each 30 seconds to say a little bit about the problem that you are most interested in. I think we've heard some of this come up in the Q&A, but why don't we do it alphabetically? So you know, this could be a problem that you think new PhD students would benefit by working on. So Akshay.
Sure. Yeah. So I think one thing that I would encourage PhD students to do is, with regards to RL, I would encourage them to find, say, a RL problem that they can try to model and understand, and figure out what kind of structures are present in that real problem, and then work on studying how to design algorithms that capture those structures.
Okay. Asli.
My advice would be, if they are interested in learning, especially long text generation, or long or short text generation, is to focus on methods where evaluation is the key, in my opinion. The next thing that we need to work on, explainability, explainable reasoning, and finding out like why this sentence is generated. I don't know how, none of us do at this point. We have some methods that we know how, but we need to work on that. So that will be a very, very interesting direction. Also, ethical issues. There's a lack of systematic methods for evaluating how efficiently these NLG systems, NLG meaning natural language generation systems, can actually avoid these improper or offensive language. How do we actually build these systems, especially important for production systems?
Yes. Great point. When you generate language, you will hear interesting things. Dan.
Let's see. I'll say three things for 10 seconds each. The first thing is grounding, thinking about how we can relate all of these latent representations that are learned in current models to grounded contingent facts inside a database that may change and need to reflect truth. The second is modularity. We build these very large systems that are very powerful and end-to-end, but one of the first things we learn in computer science is to build big, powerful tools, you need to be able to modularize and abstract. How do we get that? How do we get that power on top of what we already have? And the last thing to think about is data. When you have a PhD student, often you think about the data as being, it appears as if by magic and it's static, but in the real world, you start with no data, and then you have a little bit of data, and then you start getting more data, but your early data starts to decay because specs are changing and the world's evolving. And there's a lot of challenges here that I think go a little bit unnoticed, but are very, very real research problems that impact very greatly on real systems.
Okay, fabulous. Thanks, Dan. Katja, you get the next to the last word. I get the last word.
Now, I have a very challenging task on following amazing speakers, and I very much agree with all the aspects that you've already brought up. So maybe I'll just add one more thought. There are applications that are possible today. Also think about the kinds of applications that you would like to enable and what's missing in the current research directions to enable exactly what you would like to work towards.
Okay, thank you, all of the speakers. And to the audience as well. We've reached the end of today's technical session. Again, I apologize for the technical difficulties in syncing the audio and video across different platforms, but we will post the synced videos for attendees, hopefully later today, and for the public shortly thereafter. Thank you all for your attention and engagement with the speakers. The Frontiers in Machine Learning event will resume tomorrow morning at 9 a.m. Pacific Daylight Time. And the theme tomorrow is going to be security and privacy in machine learning. There'll be sessions on confidential computing, security in the face of adversaries, and moving beyond fairness to social equality. So an amazingly broad span of topics that all talk at the high level about security and privacy. I hope you can join us again tomorrow, and thank you very much for attending today.